Hi everybody, today we're going to talk about arc length. We'll also bring in the ideas of linear and angular speed as an application. In the last video, we looked at an arc. And when we look at the arc, we look at the angle that it passes through. So we start at the origin as our initial side, and then we move up to our terminal side. If we look at an arc for embedded circles, we can see that the angle that's being passed through is the same for both of the circles, but the length of the arc is different. The amount we're going around is much bigger for the outside circle than it is for the inside circle. Let's add some definitions to help us with this discussion. We're going to use the letter S to stand for arc length. The arc length will be related to the radius r of the circle and the angle theta that it goes through. Formula is S is equal to r times theta. It's important that you put theta in radians, not degrees, when you do this calculation. Let's try an example. Let's find the arc length of a circle with a radius of 8 centimeters subtended by an angle of 115 degrees. Our formula is S is equal to r times theta. We need to change our 150 degrees over to radians. To change to radians, we're going to multiply 115 degrees by pi over 180. I'm going to leave this as 23 pi over 36. I like to use exact numbers as much as possible. Now I have S is equal to 8 centimeters times 23 pi over 36. At this point, I'm going to go ahead and plug the whole thing into my calculator, which gives me 16.06 centimeters. Notice the units here. The units for the arc are equal to the units for the radius. So I had 8 centimeters as my radius, so I'm going to use centimeters for my arc length as well. Related to arc length is linear speed. Linear speed is calculated by finding the distance traveled, which we're going to call S, divided by the time of the travel, t. Our equation is v is equal to s over t. V is velocity, so velocity is distance over time. When looking at circles, our distance is s, the arc length, and our unit of time is still t. Let's say a car is on a circular racetrack that has a diameter of 0.5 miles and completes a lap in 45 seconds. Let's find the linear speed of the car. So to find v, we first need to know what s is. S is equal to r times theta. Notice it says the diameter is 0.5, which means the radius is 0.5 miles divided by 2, which is 0.25 miles. Theta is going to be equal to 360 degrees because it says the car completes a lap. Remember, 360 degrees is equal to 2 pi. Our S is going to be 0.25 miles times 2 pi, which says S is 0.5 pi miles. Now that we know S, we're ready to calculate V. V is going to be equal to S, which is 0.5 pi miles, divided by the time, which was 45 seconds. Putting that in the calculator, I get 0.035, and this is miles per second. As you're doing the homework, make sure you're paying attention to what they ask for the units in the answer. Sometimes it might ask for miles per second, sometimes it might ask for miles per minute, or miles per hour, so make sure your units match the units they ask for in the homework. Let's take a bigger example. Carlos spins a playground merry-go-round by holding a handrail and standing 3 feet from the center. Eddie stands 1.2 feet from the center and holds onto a rail as Carlos runs at a speed of 20 revolutions per minute. Find the linear speed in feet per second of each person. I drew a diagram of our scenario. We have an inside circle with a radius of 1.2 feet, which shows how far Eddie is from the center of the merry-go-round. We have an outer circle with a radius of 3 feet that shows the distance from the center of the merry-go-round where Carlos is standing. To find the linear speed, we need to know S over t. So S is our arc length, which is our theta, and then we divide by time. And notice that we can separate this to r times theta over t. So r is the radius, theta over t could be our revolutions per minute, which is what I'm going to do in this situation. So our radius for Eddie is 1.2 feet, our theta is 20 revolutions per minute. We want to first start by converting the revolutions into radians. To make the conversion, I write in 2 pi over 1 revolution. What I want to do is make sure that I cancel the revolutions and bring in my radians. I also want to give this answer in feet per second, so I need to switch over from minutes to seconds. So I'm going to multiply by 1 minute is equal to 60 seconds. You can see here that the minutes are going to cancel, the revolutions are going to cancel, then my final answer will be in feet per second. Putting this into the calculator and rounding to 2 decimal places, I get 2.51 feet per second. The only thing I need to do to switch from Eddie to Carlos is change the radius of the circle. So instead of 1.2 feet, I have 3 feet. All the other conversions stay the same, so I simply put this into my calculator, and I get that this will be equal to 6.28 feet per second. So you can see there is a much bigger linear speed for Carlos standing further from the center than there is from Eddie being closer to the center of the merry-go-round. Angular speed looks at the rotation of the angle. So the angular rotation per unit of time of an object is called the angular speed. It's denoted by the Greek letter omega. Omega is equal to theta over t, so again we're doing a comparison to time. This time, instead of looking at the distance, we're looking at the angle. Let's connect this to our other equations we've used so far. So we said the angular speed, v, is s over t, and s is equal to r theta. So if we write that v is s over t, but that s is r theta, then we have v is r theta over t. But we just found out that theta over t is equal to omega. So substituting omega in for theta over t says that v is equal to r times omega.
Our last problem says a car with 32-inch diameter tires is traveling at a rate of 45 miles per hour. We want to find the angular speed of the wheels in radians per minute. Let's start by looking at our formula. V is equal to r times omega. We know that v is 45 miles per hour, and we can find r because we have the diameter of the tires. We just need to find omega, the angular speed. We can isolate omega by dividing the velocity by the radius. Before we calculate omega, we should first deal with the units for the velocity. We're given miles per hour, and we want our final answer to be radians per minute. Also notice that our diameter is in inches, so for us to be able to divide by inches, we need our units for velocity to also be in inches. We're going to change miles per hour to inches per minute. We're starting with 45 miles per hour. We know there are 5,280 feet in every mile. Then, to convert from feet to inches, we'll multiply by 12 inches in every foot. Here we can cross out the miles, we can cross out the feet, and we now have inches per hour. We want to change that to inches per minute. To do our time conversion, we multiply by 1 hour over 60 minutes. This gives us a total of 47,520 inches per minute. Now that our velocity is in the right units, we can move on to find omega by dividing by r. We were given that the diameter of the tire is 32 inches. We just divide by 2 to get the radius of 16. Omega will be 47,520 inches per minute over 16 inches. We can cancel the inches and reduce the number to 2,970, and this will be in radians per minute. By default, our units will end up in radians per unit of time when we use this formula. We really saved a couple steps of dividing by the circumference, then multiplying by 2 pi when we use this formula. So our overall answer is 2,970 radians per minute. Let's do a second part to this question. Let's determine how many revolutions per minute the wheels turn. We know our angular speed is 2,970 radians per minute. We also know that 1 revolution is equal to 2 pi radians, so we really just need to divide by 2 pi. We'll write it this way: 2,970 radians per minute times 1 revolution divided by 2 pi radians gives us a total of 472.69 revolutions per minute.